Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 10 and will be doing the part 2 of current versus voltage characteristics of MOSFET. Let's revisit the basic equations of MOSFET. We have seen in our previous discussion that the drain current in the linear region is given by this. I have written here knowingly mu p because it is for p type semiconductor. For an n type semiconductor, we have already seen that the current will be equals to mu n C ox by 2 into W by L into 2 times VGS minus VT0 into VDS minus VDS whole square. This is for an n type semiconductor and this is for the p type semiconductor. So, this is for PMOS and this is for NMOS. This is in the linear region of operation. Linear region is where VDS is less than VGS minus VT0. We come to the saturation region. This is for again for PMOS. Let me write down for NMOS for the sake of completeness. For NMOS you can write down the same quantity, that it is mu n C ox by 2 into W by L into VGS minus VT0 whole square. And why is it plus sign? You need to understand why, because it is a PMOS. PMOS has got a negative threshold voltage, right, remember, and therefore minus of minus will become positive, right. And why we are writing SG not GS? Because it is PMOS with source with respect to gate we are writing. So, if you take gate with respect to source, it will be a negative voltage. Source with respect to gate will be a positive voltage. Why? Because source voltage will be always equals to 0, right, and gate voltage will be negative. So, when you subtract this, minus of minus Vg will come out to be Vsg will be always a Sg will be always a positive quantity. So, that is the reason. This is for PMOS, actually I am showing it to you, and this is for NMOS, right. This is for NMOS which you see. Now, let us come to a very important sort of parameter which we use in MOSFET, and that is known as transconductance, right, which is GM. Sometimes we write as S and B. We will explain to you later on what do I mean by that, but let me write down what is the meaning of GMS. GMS is basically defining as transconductance in the saturation region. So, the obvious question asked is what is transconductance? Now, so if you look very carefully in the MOS device, when you apply a drain voltage, the current is flowing from source to drain, right. So, always the current will flow from source to drain. There is no other way the current can flow except the leakage current through the oxide layer or through the substrate. But assuming that it is only flowing through the drain side, then the direction of the current is always in the longitudinal direction, right. But the potential which you are applying to form the current is basically on the transverse side, right. So, that is the reason it is known as a transconductance. I am trying to find out the variation of the drain current with respect to change in the gate to source voltage, and therefore, we define GMS as del ID sat del VGS. So, if I differentiate this quantity with respect to VGS, I should get the value of GM, and that comes out to be, I am not doing it in the class, but you can actually look mu n C oxide W by L into VGS minus VT. And therefore, and quite interestingly, GM is actually a sort of proportional to VGS, and it is almost a linear function of VGS. So, VGS minus VT what? It is basically my V overdrive, remember. So, basically if you write down this whole quantity, I can write down this to be equals to mu n C oxide W by L into V overdrive. So, higher the V overdrive, more is the transconductance. Now, you will ask me why transconductance is in a sense important. It is important because it shows to me how sensitive is your device to variations in the external bias. External bias means input signal. So, if the GM value is large, it implies that for even a small change in the value of gate to source voltage, you get a substantially large value of change in the drain current, right. and that is the reason the transconductance is a very, very important sort of parameter which one has to look into in terms of device modeling. So, this is for saturation region, right, and therefore, I see a linear dependency of Gm with respect to Vgs minus Vt0. In non-saturation region, which is basically your the region where we are left side of the Vgs minus Vt0, we define Gms to be equals to this quantity again, right, and del id sat. So, in the non-saturation region it will be Vgs, so it will be this will not be the equation which you are seeing here. So, I can actually differentiate this equation in the non-linear form, this one. So, I need to form out del id as del Vgs, you will form out, and you can get the value from here, this equation from here, it will come out to be the same thing here. Now, you see in both saturation and in non-saturation region, it is dependent on the overdrive actually, and also depends upon the aspect ratio. So, if your aspect ratios are large, you could expect to see a large value of your GMS, right. Let us look at the final expression, and that is known as threshold voltage, and is given by this formula here, that Vt equals to VFB plus 2 phi FB plus a quantity given here. So, this is 2. So, I am assuming that I am into sort of a strong inversion, right, and therefore, my psi s is approximately equals to 2 times phi Fp. Since my psi s is actually 2 phi f, so I have replaced this expression, the last one, right, by this value. Actually, if you look carefully, let me rub this portion and explain to you. If you let us concentrate here, it is given as 2 epsilon into q times N A, right, into psi s divided by C ox square root of that. Now, in strong inversion, when the threshold voltage has been reached, this psi s is actually replaced by 2 phi f, because twice the Fermi level dip will be there in the Fermi level with respect to the intrinsic Fermi level. So, these are the few important basic equation you need to just keep into your mind while applying for assignments, while applying for all numerical examples and so on and so forth. First thing is linear region, drain current in saturation region, transconductance in saturation region, transconductance in linear region, and then the threshold voltage. How to define threshold voltage, where VFB is the flat band voltage and 2 phi f is already known to you. With this basic equation known to you, you should also be in a position to actually now write for NMOS and then extract it for PMOS or vice versa, right. So, these are all for N channel or P channel enhancement mode MOSFETs, right. So, this takes care of our basic understanding of IV characteristics of MOSFET. Let me switch to a new topic in MOSFET, and that is known as capacitance in MOSFET. Now, there are two types of basic capacitances in MOSFET. One is known as the gate capacitance here, right. One is the gate capacitance here, another is the junction capacitance here, right. So, you have two types of capacitance here, gate capacitance and junction capacitance. From where are these capacitances coming into picture? So, typically when you talk of gate capacitance, we talk of gate to source overlap, gate to drain overlap, and gate to channel. And it will be easier for you if you actually see how formation takes place. So, let us suppose this is there, let me rub it for you. So, let me draw for you. I have this oxide layer, metal layer, and what I have done is, this is my N plus and this is my N plus. This is my source, this is drain, right, and then you have these regions coming into picture. This is P type substrate, assuming it to be an enhancement mode MOSFET. So, this is gate. Now, you see, if we apply so this is N plus means high doping concentration of electrons here. Similarly, N plus here will be high doping concentration of large number of electrons will be there. So, if you apply a positive gate bias here VGS, then this metal will be full of charge carriers, and you will also have charge carriers here separated by a dielectric at these 2 points. So, this is my CGS, gate to source, and this is my gate to drain, CGDs. So, if you look at the gate and the source, the capacitance between them is because of this overlap. Similarly, gate to drain, if you look here, is nothing but the overlap between gate and drain. So I have a gate to drain overlap. Why is it overlap? Because the gate and drain are overlapping with respect to each other. If they were not overlapping, this will not come. But in all practical devices, this happens, that there is a short overlap which happens, because of which you will get CGD and CGS, gate to source, right. There will be also a potential, or there will be also a potential with respect to bulk, because you see your body or bulk is there, the fourth potential or a fourth terminal device. So what will happen, the gate will also try to talk to bulk through CGB, gate to bulk. Gate to bulk is what? This, you have a depletion region here, remember. So this depletion region, there will be oxide layer here, so it's C ox and C depletion in sort of series to each other. That will be CGB, gate to bulk, right, which you see here. And then you will also have source to bulk. Why source to bulk? Because source is grounded, right. If you somehow or other give some potential on the bulk side, you will have some source to bulk. In all probability, this is almost 0, because source to bulk can only happen when you provide a bias either on the source side or to the bulk side. Since at this stage we are not providing any bias, so I am assuming that there is no depletion region formed here, and therefore this can be considered to be equals to 0. However, drain to bulk will surely be a big component, and the reason being that typically this as actually because of a positive bias given on the drain side, right, and you are reverse biasing this drain to bulk potential. It is almost behaving like a reversed biased PN junction diode. So out of all these three, I can show you that CGD, gate to drain, gate to source, gate to drain, gate to source overlap. I will discuss gate to channel later on. These are known as gate capacitances, and source to bulk is this, source to bulk, and drain to bulk are all my junction capacitances. These are known as junction capacitances, and this is known as gate capacitance on the left hand side. Now what is a channel capacitance? Let me explain to you what is a gate to channel. Gate to channel is, suppose I have applied a gate bias here which is larger than the threshold voltage of the device. There will be a channel, as I discussed with you, inversion layer will be formed, and there will be a large electrons which will be flowing through this region. So now you have this charge and this charge separated by this distance, and as a result what will happen is gate to channel. But please understand and be very careful that all these capacitances are bias dependent capacitances. Why? Because as you change the bias, since the depletion thickness changes, the value goes on changing, right. Not for the gate capacitance per se, but so surely for the junction capacitances. For example, CDB, if you take an example, go on increasing the value of the drain potential, and what you will see, that the drain potential will make the reverse bias stronger and stronger. Thickness goes on increasing, capacitance starts to go down, right. And that is quite an interesting way of looking at the capacitance in a basic MOS device. So we have learned two things from this takeaway from this slide, that we have a gate capacitance and we have a junction capacitance. Gate capacitance is between gate and source, gate and drain, and gate and channel, and junction capacitance is between bulk and drain, bulk and source. We have also understood that between source and bulk, if both are grounded and we assume that both are properly grounded, then there will be no CSB, but there will be CDB available to you, right. And therefore, and what is the reason for studying this? The reason for studying this is that if we know what the capacitance values are in a bulk MOSFET, we can actually do a good amount of very decent and accurate transient analysis for a MOSFET, right. We will not do a DC analysis. When we do a transient analysis, these factors will come into picture. Let us deep dive into gate capacitance and overlap capacitance. As I was discussing with you, once this N plus region is my source, right, and this is my drain side. Now the overlap capacitance which you see here, right. So if I assume that XD is the overlap length on each side of the channel, then L effective will be L drawn minus 2XD. Why 2XD? 1XD here and another XD here. This is my effective channel length. So effective channel length is basically L drawn this is the drawn channel length, right. This is the drawn channel length which is under the gate. This is the drawn channel length, and the effective channel length is between the source and drain, and if you remove this XD here, right. Now there can be two types of overlap capacitance. One is extrinsic, another is intrinsic, right? I will just show to you what is an extrinsic and intrinsic. Look at this gate, right? This gate is having a potential, let's suppose a positive potential. Let me give a drain also a positive potential, and let me ground the source. Now if you just look, and obviously I am assuming that the gate and drain potentials are not equal, then I will have one capacitance going through this, through the overlap. Another capacitance can also work like this, right, which you see CGS OI overlap. So CG, gate to source overlap, this is intrinsic, right? Gate to drain overlap with in I is capital is intrinsic, right? And why? Because the two charge separated by a distance, air is the separation here. So this is an external capacitance, and the ones which is going through XD is known as an overlap internal capacitance, right? So within the gate capacitance structure also you will have an extrinsic you have an external capacitance, external overlap capacitance, and an internal overlap capacitance. The internal one or intrinsic one will be given through XD, right, and the outer one will be given through these two. The outer one will be through this, and the internal one will be through this. So it makes very important sense that if you therefore tend to make the overlap region larger and larger, right, you end up having larger and larger capacitance being generated. So it is always advisable that to keep your cap low, try to make a self-aligned structure, which means that the gate does not overlap with source or drain. The more it overlaps, the more difficult its lives become for you in terms of having low capacitance, effective low capacitance. Now please understand one more thing which I have not dealt here, but you need to consider that as well in your further studies. That is that as you start increasing the drain bias, right, as you start increasing the drain bias, what happens is that, so let us suppose you want to increase the drain bias here, right, you are going on increasing it. As you are going on increasing it, the depletion region here actually becomes larger and larger. It becomes larger and larger, and your effective channel length still goes on reducing. So your L effective, which I have shown here, L drawn minus 2 XD, L effective will be much lower even than that, right, and therefore your W will increase or current will increase, because current is directly proportional to W by L. Let us look at the quantitative analysis of my overlap capacitance. If you look at CGSO, gate to source overlap or gate to drain overlap, it is nothing but Cox into W into XD. Why Cox? Cox is this capacitance here, oxide capacitance, multiplied by XD, the length, this area, this is oxide capacitance per unit area, remember. So basically if you multiply this with area, you get the total capacitance. So I get overlap capacitance given by Cox into W into XD. W is where? W is in the third dimension. So if you look at the right hand side figure, this one, this is the figure where the MOS cap, which was like this, which is shown to you like this, right, like this, has now been flattened. So you have flattened your device. Once you have flattened your device, the third dimension appears like this. This is the W. So you see this is the W value which is there with you, and this is your length LD, the drawn length LD, and this is your depletion or the overlap length XD here. This is the polysilicon gate which is overlapping between the two source and drain. If I assume that the doping concentration is exactly the same, or the overlap length is exactly the same on the both source side and drain side, and XD therefore is constant, therefore I can safely say that the value of CGSO and CGDO will exactly be the same. It will only depend upon the value of XD, W and Cox. This is the concept of gate capacitance overlap. So let us now come to the total overlap. Now I told you that overlap capacitance and channel capacitance, two components are there, and we will go one by one looking at what will happen of the capacitances when you go to cutoff, when you go to saturation and accumulation. Let us go one by one. Let us go to the first stage, and that is known as cutoff, right. Cutoff is what? When VGS is less than the threshold voltage of the device. Your device is cut off, there is no current flow, so there is no channel connection, and therefore my CGS and CGD is nothing but the overlap capacitance and given by Cox into W into XD, which we have already studied in our previous slide, right. And gate to bulk will be Cox into W into L effective. Why? Because gate to bulk is this capacitance CGB, this one. So you see it is nothing but C oxide into W into L, right, L effective. This is the L effective value which you get, and that's the value you get, and therefore the total gate capacitance will be given as C ox into W by L, right. The total gate capacitance CG will be C ox into W by L, CGS and CGD will be C ox W into XD, and CGB gate to bulk will be C ox W into L effective, right. So CGB and CG will be almost the same value, because L and L effective can be taken to be almost the same value, though for very short channel devices this is not true. Let us come to the linear mode of operation, right. Linear mode of operation, let us come to the point. Linear is when the channel is spanning right from source to the drain. So you have a thin layer of channel which is being formed, and right from source to drain you are fanning. So what people, the way various authors have gone through it is that they assume that the channel capacitance is split equally between source and drain. So what we do, we write CGS and CGD is equal to 1 by 2 C ox into W by L effective. Why gate to bulk is 0? The reason it is 0 is that now you have an inversion layer which actually starts to screen between the gate and the bulk. So your gate to bulk becomes effectively equals to 0, right. What is the change which you see? The change here is 1 by 2 C ox into W by L effective, which you did not see in the previous case. This is for the linear mode of operation, when you have a constant current being formed, not a constant current, but a current which is directly proportional to the value of VDS. So it is linear region of operation. Now let us come to the saturation region of operation, and the channel is therefore pinched off. What has happened is that I have source drain, and what has happened is the channel which was higher here is now pinched off, or it has gone to this particular place because of large value of drain to source voltage. Then what authors have said, and this is a research topic, again debatable as of now, we have the total gate to drain capacitance is W into XD into C ox, gate to source is 2 by 3 C ox into WL effective plus C ox into W XD. I will explain to you what do I mean by that. So gate to drain is the reverse bias junction drain. So just I need to find out the value of XD, which is the overlap length, multiply that with W with C ox, I get CGD, right, very straightforward. Gate to source is the crux here, that you will have C ox into WXD, which is the first component which is there, but you have an additional component coming here. And the reason this component comes into picture is that when in the saturation region, when the channel is actually pinched off at the drain end, you still have a substantial depletion region on the source side, right, small depletion region on the source side, which contributes this much amount of oxide capacitance. And CGB, obviously since the channel is formed, screening effect takes place, my CGB is exactly equals to 0, this is equals to 0. So the total gate capacitance can be written as this, right, 2 by 3 C ox WL effective multiplied by this plus this, and therefore it is 2 times C ox WXD. So the total gate capacitance which you see is 2 by 3 C ox W into L effective plus 2 C ox into WXD, width into XD, which we get. This we get as the total amount of capacitance in the saturation region. And therefore you see quite interestingly that these capacitance are all bias dependent capacitance. So if you are biasing a device in the linear region, in saturation region, or in the cutoff region, the capacitance will go on varying. So the various capacitance, just let me put it on the form of table, so that it's easier for you to handle it. This is gate to bulk, gate to source, gate to drain, and CG is equals to CGS plus CGD plus CGB. When you come to the cutoff, right, when your actually device is in the off state, obviously gate to source and gate to drain will be 0, right, because the potentials are anyway very strong. And what you get here, a gate to bulk will be equals to the oxide capacitance, correct. Why? Because there is an oxide capacitance, I have applied a gate voltage, but bulk is grounded, and therefore it will be even less than oxide capacitance, and therefore my total gate capacitance will be equals to C0. In the linear region of operation, it becomes oxide capacitance by 2, oxide capacitance by 2. So if I add these two together, I get C0 here. In saturation region, I get 0 in CGB, and you know the reason why it is 0, because of the screening effect here. And therefore it is 2 by 3 here, and then it is 0 here. gate to drain, and therefore if you add these two together I get 2 by 3 C0, which means that as you move from cutoff towards saturation, that means when you vary the value of drain to source voltage, your capacitance initially was C0 large, and it becomes 0.66 approximately of C0 at saturation, right. So this same thing is being replicated onto the left side here, that in the off state it is nothing but C overlap. As you move into the saturation triode region, this is the value of the overlap, right, and this is the value of your CGS, this is the value of your CGD, and so on and so forth, right. So this is threshold voltage, and this device switches on from here. This is threshold voltage plus VDS goes into saturation region of operation. Now if you look at this graph here on the left hand side, it tells me an interesting story, that since the capacitance is basically bias dependent in a sense, you end up having the values depending on the Cox value. So one parameter which goes common across the whole board is your oxide capacitance. So if you take your oxide capacitance to be low or high, I will be able to maintain a good value of CGS and CGD. Similarly, another parameter is C overlap, the overlap capacitance which comes because of XD, or the overlap distance which you see in front of you. This overlap is primarily because of lithographic steps problem, and you will have some overlap regions coming into picture. So what we have learned from this discussion, at least from this discussion, is that you will always have a bias dependent capacitance. Let me come to the gate capacitance is a function of voltage. We have already done this, but I will just give you a graphical presentation of that. If you look at the left hand side, if you plot the value of gate voltage, then when you take VGS equals to -1, you are into accumulation region of operation. Accumulation basically means that the output resistance will be, for gate to bulk, will be C0. We have already seen that. It will be C0 for CGB. But as you start to increase your gate voltage, you see the blue dot, it starts to go down. Gate to bulk, or even the black one, starts to go down. And the reason it starts to go down is screening effect happens. At threshold voltage, when you have the maximum screening effect taking place, that component actually goes to a 0 value, and then gate to channel starts to increase. Why? Because now the inversion layer has been formed. Because of the inversion layer, there will be large amount of inversion charges available to you, which will result in a larger capacitance between the gate and the channel, and that's the reason you see your CGC, the gate to channel, goes on increasing depending on the value of VGS. Look at the right hand side figure. I am trying to show you the VDS dependency here. So we are plotting basically VDS by VDSAT. So we are plotting VDS with VDS divided by VGS minus VTH, this VTO, or with threshold voltage. We are plotting that. So once it is 1, it basically means you are in the saturation region. This one is and this is the linear region of operation, right. In the linear region of operation, I told you when VDS equals to 0, which is on the left hand side, you automatically have your CGC to be equals to 0, C0, oxide capacitance. However, your gate to source and gate to drain is half. Remember why half it is? Because I am assuming that's perfectly symmetric device. But as you go on increasing your VDS value, the gate to channel starts to fall down. Very well known reasons for you. You have larger and larger amount of carriers being formed. However, CGS goes up and CGD goes down. The CGC goes up to 2 by 3 C oxide, and CGD goes to 0 at saturation. Why at saturation it goes to 0 CGD? You try to figure it out, because now you do not have any channel to talk to. So there is no overlap available, and that is the reason your CGD goes down. But your CGS, gate to source, has still some value available, because the tapering of the channel takes place more towards the drain side rather than the source side. And that is the reason you see it becomes 2 by 3 C0 here. So this is 0.2 by 3. What does it so what does it tell me overall? It tells me that if you look at this point, it tells me that bias dependent on both gate to source as well as drain to source, and the value goes on changing with the applied bias. That is one thing which you should know. Now let's finish off this discussion on this talk by telling you what is the junction capacitance of a MOSFET. we have already known that the junction capacitance of a drain to body capacitance, drain to body, will be basically reversed bias junction. So, this is CDB0. CDB0 is when your bias voltage is 0, that is your CDB0 capacitance, divided by 1 plus VDB by V0, right. This is what we are assuming, that the source and drain diffusion is there, and source to body again will be exactly the same like a PN junction reverse bias. Rather than drain to bulk, it will be source to bulk voltage by V0. V0 is a constant value which you see, right. Uh, and CDB0 and CSB0 is drain to bulk and source to bulk at 0 bias, right, and that is what we have written here, if you look at this particular point, right. With this, with this we come to the end of this lecture, and let me recapitulate what we did in this case. First of all, we understood in this lecture the various forms of, we recapitulated our equations of MOSFET, right. We looked into the equations of MOSFET, we looked into the various now capacitances of MOSFET, cap of MOSFET, and we saw that there are two types of capacitance. One is the junction capacitance, right, and another is the non-junction capacitance, which is basically the capacitance forming between gate to source and gate to drain, right. And then we saw how these capacitance CGS and CGD and CGC, drain to bulk, this is the junction capacitance, and source to bulk, they vary as a function of applied bias VGS and VDS, and what is the reason for that bias. And then finally we ended up understanding the junction capacitances, right, and how it is. So, junction capacitance is simple, reversed bias PN junction diode, which you have already studied, will be, the values of the capacitance will be exactly the same. So, with this, let me finish this lecture. Thanks.